spent an awful lot of his research life researching on things like axiomatic semantics, which I told you that you might get in fourth year if you're interested. And the only way you can do that is if you know a lot about operational semantics, which you know is the first part of the course, and Lambda calculus, which you'll be telling you now. As you can, this has gone. As you can see, we were having problems, and in particular, John had some really nice animations that he's not going to be able to show you because he whacked it on a PDF and put it on the Microsoft machine. So over to John.
Cool, right, well, thank you very much, Philippa. So, yes, I'd like to begin by thanking Philippa enormously for giving me the chance to take a couple of her lectures in her wonderful course. And not only is it a few lectures within a really interesting course, but actually it's the best bit of the course, so I'm thrilled to get the chance to present this bit. The Lambda calculus is extremely cool, and it's a very serious candidate for the coolest bit of computer science, full stop. People go absolutely mad about the Lambda calculus, not least this gentleman here, who not only has a Lambda calculus t-shirt, but also a Lambda calculus cuddly toy made by his daughter, he tells me. And in fact, this gentleman will play quite an important role in this lecture, just a couple of lectures. His name is Phil Wadler, and he is very well known in the computer science community because he had a very big hand in the design of both of the languages that I think you've studied in your degree so far. Java, who's a big part of that, and the design of Haskell. And if we look at these languages just for a moment, you see that these languages are really quite complicated. Here's just a tiny, tiny fragment of the syntax of Java. I've probably got it completely wrong, but just to give you a flavor, this is like 100th of the language. But you see you've got if blocks, you've got try, catch, finally, whatever that means, while statements, lists of statements. Even Haskell, which you might think of as a much more puristically designed language, even that has a whole load of complexity. You've got let statements, you've got if then else, lists down here, booleans, pairs, triples, tuples. There's a lot going on. And one of the most identifiable aspects of the Lambda calculus is that the entire language can be expressed in just 3 lines. So Lambda terms M take one of just 3 forms. They're either a function abstraction, that is, a function that takes an input, say x, and returns a lambda term m, or it's a function application. So this is m. This term here is a function, and this is the argument to that function. And we don't bother putting brackets around our arguments because we're grown-ups here. And then the other type of lambda term is just a plain variable. And that's it, that's the whole language. So the Lambda calculus is cool because it is the simplest programming language in the world. So not only is it simple, but it's incredibly powerful. In fact, anything that you can program in any other language can be programmed in the Lambda calculus, just using that impoverished language that I just showed you. So that's pretty stunning. And later on in this couple of lectures, I'll show you how you can go about recovering all of these features that we seem to be managing without. In particular, I didn't even include numbers in that grammar there. It's also cool because you can use it as, if you like, a training ground in the study of bigger real-life programming languages. So a lot of the issues that arise when you're designing a language can be traced back down to the Lambda calculus, where they can be studied in a more fundamental form and then scaled up again. So questions like, should my language use types? When are 2 computer programs equivalent to one another? When can a program fail to terminate? When I pass parameters to a function, should I do call by value, call by name, something else? All of these questions can be studied in the context of the Lambda calculus. So this couple of lectures is going to be divided into 3 sections. So I'm going to begin by talking about the syntax of the Lambda calculus. So what do Lambda calculus terms look like? Secondly, I'm going to look at the semantics of the Lambda calculus. What do Lambda calculus terms do? What do they mean? And then thirdly, having defined what the Lambda calculus looks like and what it does, we'll look at how you can use the Lambda calculus, in particular to recover these features that we thought we might have lost. So we're going to begin with the syntax. So up here, I'll give you a little reminder of what the syntax was, in case you've forgotten it already. And I just want to begin by showing you a few Lambda calculus terms. So here is a Lambda term. It's a function. It takes x, and it returns x. So it doesn't really do very much. You could call this function the identity function. Here's a Lambda term. It is another function. It takes x, and this time it returns y. What is y? I don't know. But we can write it. So here's a slightly more complicated Lambda term. It's a function that takes x and returns x, and this function is then applied to another function that takes y and returns y. Okay? We can also have something like this. This is a function that takes x and returns a function that takes y and returns a function that takes z, and finally returns x. Note that when I write, so sometimes when functions like this are written down, these sequence of lambda symbols can be abbreviated like this. I won't actually do that in these slides because I think the version on the left is a little bit more readable, but be aware that sometimes we'll do this. And here's a more complicated lambda term. No idea what it does, but you can see the kind of thing you can write using this language. Yeah, I don't think I'll spell it out, but I'll just draw your attention to this bit here. Here we have the application rule done twice, so 3 terms straight after one another. And just be aware that when you see this, the bracketing, quite important, has to go to the left. So M1, M2, M3, the brackets go around M1 and M2 like that. And this should be familiar from Haskell. This is the same behavior that you saw there. So in these lambda terms, you can see already that there are a couple of different ways that we're using the variables. So up at the top here, this x appears inside a lambda x. And we'll say, because of that, we'll say that this is a bound variable. We're going to color it green. On the other hand, this y does not appear inside a lambda y. So it is not a bound variable. In other words, it is a free variable. And we'll color it red, make it pop. And we can continue this for the other lambda terms. So this x here is bound. This y is bound. This x is bound. And this x is and this x is, there's some disagreement. So this one is free. So x can be bound in one place of the lambda term and then free elsewhere, as the scope of this lambda x cannot escape the brackets that it's placed inside. Y is, z is, y over here is very good, and x is good. So this brings us to our first key concept then, that when you have a lambda term that perhaps looks a little bit like this, we'll say that the lambda x here, this is a binder, the x that appears inside it is a bound variable, and the y here doesn't go inside the binder, so that is a free variable. Okay, so free variables are pretty important in this when we're studying the syntax of the Lambda calculus. And it's sometimes handy to have a little function, which we'll call fv. This function will extract from any given lambda term the set of free variables that occur inside it. So, for instance, free variables of lambda x dot y, just the set containing y. Very straightforward. And in particular, when the free variables set is empty, we'll say that M is closed, sometimes called a combination. This brings us then to the main concept in this section, which is alpha equivalence. This captures the idea that if you have a lambda term like lambda x dot x, and another lambda term, lambda y dot y, they're clearly different lambda terms, they're visually distinct, but there's a sense in which they should be treated as the same term morally. And this is what alpha equivalence captures. So alpha equivalence is just the idea that if two terms only differ because you've renamed some bound variables, then they're alpha equivalent. And alpha equivalence occurs in other programming languages as well. So here's a bit of Java or C, C++, I don't know. I'm not sure what the code does, but it doesn't really matter. The important bit is that here we are declaring a variable called I, and then we're using the variable later on. So this, you can kind of read this as a lambda I, in a sense, here. And so alpha equivalence kind of captures the idea that I can change this I into a J, and all would be fine. But you've got to be a little bit careful when you're renaming bound variables, because you don't want to go changing this to, so that's happy, yes. And then you don't want to go changing this to x. This would be a mistake, because we already had x appearing, so that gets this back. So this x was already free, and we made it clash. So you've got to be a tiny bit careful. So back to the lambda calculus then. We could ask questions like, are these two terms alpha equivalent? I'll give you a minute to think about that. So we've got lambda x, so the function takes x and returns x applied to the function that takes y and returns y, all applied to y. Is that alpha equivalent to lambda y dot y applied to lambda x dot x applied to x? What do we get? So what we can do to help us determine whether we think these are alpha equivalent or not is we can do the free and bound variables analysis. So the colouring red and green that we did in this last slide. So here are all of the, so x and y here are bound, y is free, and likewise over here x is free. And once we've done this, then it becomes very clear that these terms are not alpha equivalent because they differ in their free variables. Alpha equivalence only allows you to rename bound variables. You can't go changing what you're doing with free variables. They're not alpha equivalent. What about this one? All I've changed here is I've changed this x now has become a y. Have I fixed it? Are these now alpha equivalent? Who thinks they're alpha equivalent? Let's have a look. So again, we'll colour the free variables and bound variables. It goes like this. So x, y are bound. This y is still free. But note now that this y over here is bound because it occurs inside this lambda y. Okay? Which means that these terms are not alpha equivalent because we've fiddled around with the free variables. Okay? So what started off as quite a intuitive, natural concept has actually become a little bit subtle. And in fact, it's worth pointing out, alpha equivalence is really, really complicated. There's a professor I know at Cambridge who has spent, I would say, at least 15 years of research basically into alpha equivalence. So this is really complicated stuff if you dig deep. Okay, third example then. Are these two terms alpha equivalent? So we've got lambda x dot x applied to lambda y dot y applied to y. And then over here we've got lambda w now applied to w, and then lambda w dot w and y over there. Hands up for alpha equivalent. Hands up for alpha unequivalent. Okay. So let's do our free and bound analysis again. So this is looking a bit better now because the free variables match up. But we can dig a bit deeper now, and what we'll do is we'll proceed along the terms, starting from the left-hand edge of both terms, just proceeding along, making everything match up. So we start with lambda x, and we start with lambda w over there. That's not the same, but perhaps we can make them the same. We could rename the x to become w, or we could rename the w to become x. In fact, we'll take a third option, and we'll rename both of them to something completely different. This is a bit more symmetric for various other reasons. So let's say we'll pick an extra variable, let's say z. We'll pick z is a good choice because z doesn't occur inside either of these terms freely. So let's do that. So I've changed this, x has become a z. This w has become a z. This w I didn't change because I said only change the free occurrences of the w's inside this term. So this one's bound, so we don't touch that. And now we're getting a bit of progress because now both terms begin with lambda z dot z. This is good. Now we've got another discrepancy here, lambda y and lambda w. So again, same trick. Let's rename both y and w to some new, fresh variable. In fact, z is a good choice here, again, because z doesn't occur inside here, it doesn't occur inside here. So let's stick with z. And there we go, we've made the two terms become completely identical just by renaming bound variables. And so the original term up here is alpha equivalent. Excellent. So we've seen a couple of examples. So now it's time to generalize. I want a general algorithm, general definition for saying, if you give me two lambda terms, are they alpha equivalent or not? So what we're going to do is we're going to have three inference rules, one for comparing two function abstractions, one for comparing two function applications, and one for comparing two variables. Variables is easiest, so we'll do that one first. So two variables are alpha equivalent if, well, they're the same variable. The thing is, when a variable occurs on its own, it's always a free variable. There's no lambda around it, so you can't go changing it. So it has to be x is only alpha equivalent to x. Okay, that's easy. Function application is also fairly straightforward. If I'm trying to compare mn to m prime n prime, then all I have to do is check that the two m's, so the two functions, are alpha equivalent, and I'd better check that the two arguments are alpha equivalent, so that the two versions of n would also better be alpha equivalent. Finally, we come to the comparing two function abstractions. So I'm comparing, the question is, lambda x dot m, is that alpha equivalent to lambda y dot n? So what we do, we pick our fresh variable z, just like we did in the previous slide, and all we require of z is that it's not free in m and it's not free in n. Having done that, we replace all of the free occurrences of z inside m with n. No, sorry. Yeah. We replace all of the free occurrences of x inside m with z, and we replace all of the free occurrences of y in n with z. It's easy to get those the wrong way around. And if the result of doing that gives you terms that are eventually alpha equivalent, then you're good. So there's one more subtlety with alpha equivalence, and that's defining this substitution thing here. So how exactly do we carry out this replacing all of the x's with z operation? So this is called substitution, and it's a little bit more subtle than just going into your text editor and saying find and replace all of the occurrences of this thing with this other thing. And that's for reasons that I'll explain now. So again, let's go back to Java for a moment. Suppose I've got some Java code. Again, it's probably wrong, I don't know what it does. but I'm trying to write some, I don't know, maybe I'm writing some Eclipse plugin that helps me do some refactoring of my code. And the thing I want to do is I have this constant e, that's the exponential constant from maths. Its value is something like 2.718 or so. At the moment, that occurs as a variable in my program, but perhaps I'd rather have that as a number in my program. So I want to replace all of the occurrences of e with the actual number. Okay, fair enough. So I'll go straight through the code, blah, 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 blah. Replace that e with 2.718. Good. Carry on. Oh, what should I do here? So this is, I shouldn't replace this, right? Because this is basically a lambda e. Yeah. Again, you're declaring a new variable called e, and then this e is now definitely not the same e. So you've got to be a bit careful with doing this substitution. Only replace the free occurrences of the variable you're trying to replace. So that's the first subtlety. The other subtlety occurs in a more Haskell-like setting. Again, this is probably not valid Haskell, but hopefully you can understand what I'm trying to say. This is a program that says evaluate 4 times y and store that in x, and then proceed to evaluate w plus 5 and store that in y even, and then finally evaluate x times y. Okay? So suppose I'm trying to do some code transformation here. Maybe I've decided that it's not really necessary to introduce this variable called x. That I only use it once, so maybe I'll just fold that down and get rid of the variable x, for instance. So what I might do then is substitute this 4 times y in for this x. And this was the point where in the keynote you'd have had some beautiful animation, and you'd end up with this. So you can imagine filling in the gaps there. Anyway, this has gone horribly wrong. Can you see what happened? The 4 times y has come in, but in moving from out here, it's gone inside the declaration of y. This here is basically a lambda y. You've moved the free y inside a lambda y, and it's gone from being free to bound. We say it's been captured. This is bad. This has changed the semantics of our program, so we don't want to do this. Angry face. So how do we fix this? Well, simple. Just rename y, the bound variable, change that to something else, like I said, and now do the and now you can substitute in, and you don't have to worry anymore. Okay, so this is now fine. Okay, so those are the 2 complexities that you've got to worry about when you're defining substitution. So with those in mind, we can now go to what is the definition of substitution. So it looks like this. Suppose I'm trying to substitute a variable, say y, and I want to replace, I want to put in m for x. But there are 2 cases. Y and x might be the same variable, or they might be different. If they're the same variable, then that's the same as saying x, but with m for x. So that's just m, right? So that's the top line there. And the other case is y and x are not the same variable. But if they're not the same variable, then if you do y, but with all of the x's replaced with m, that's not going to do anything. There aren't any x's in y. So the substitution has no effect, and so you're just left with the original term, y. Okay? So that's how substitution works when you've got down as far as a variable. The tricky case is function abstraction. So here we go, deep breath. Oh, lots of maths. Okay, so we want to do this, we've got this function lambda y.n, and we want to replace all of the free occurrences of x with m. So again, there are 2 cases to consider. If x and y are the same variable, then, so this is basically lambda x.n, then there are no free occurrences of x in lambda x.n. As soon as you've got the lambda x, then that's going to bind any occurrences of x that might occur in n. So there are no free occurrences of x there, and so we've got nothing to substitute for m, and so the substitution has no effect. Okay? That leaves us with the case where y and x are different variables, and what you do here is, so at the first approximation, you take n and you do the substitution of m for x. But you do another substitution first. You're replacing all the y's with z's. So this was the thing that I did on that second example, the Haskell, when I was substituting in. This is to get around the danger where m contains y free. Because if you just go and put m in here, then it's going to get captured by this lambda one. So that's why we introduce z, because we know that z is certainly z is going to be something that is not free in n. And there's a little get out clause here that says z and y, by taking away y from the set of things that z is not able to be, I am just about allowing z and y to be the same variable, and this will only happen in the case where m doesn't contain y, so it wouldn't have been a problem in the first place. So it's saying you don't have to do this crazy renaming every time you do a substitution, as long as nothing would have gone wrong. Okay, and finally, function application. If I want to do a substitution on a lambda term that looks like n1, n2, all I have to do is apply the substitution to n1 and apply the substitution to n2. So that's nice and simple. Cool. So this brings us to two more key concepts. We've seen alpha equivalents, two terms being equivalent if they differ only by renaming of bound variables. And we've seen capture avoiding substitution. So this is this flavor of substitution where we are worried about free variables becoming bound when you do the substitution. And so this is called capture avoiding substitution, where you rename to avoid this problem. So I'm now going to. So this is a couple of bonus slides that's slightly extracurricular. They're for your general education or something. They're just a couple of interesting topics that I wanted to share with you because they're pretty cool. Might help you with a pub quiz in 20 years' time or so. So the thing about so alpha equivalence is really a bit of a pain. I think as you've seen, we're always having to rename bound variables. And wouldn't it be nice if we could get rid of these bound variables altogether? And so this fellow, De Bruyne, I'm probably pronouncing wrong with very Dutch people here, he came up with a scheme that avoids bound variables altogether. The idea is like this. So of course it doesn't matter what name I pick for x, and it doesn't matter what name I pick for z, as long as I just use that name consistently in the rest of the time. So he says, well, how about you write your term like this? Okay, so just have a blob and use an arrow to say, I don't care what name you pick here, just as long as this guy matches up with this guy. So you're using these arrows to sort of reflect the relationship between the various variables and where they are bound. This is kind of neat. And if you don't fancy programming with a sort of drag and drop arrow things, which probably most people don't, then you can use a scheme with numbers instead. So that would look a bit like this. So if you have lambda x.x, in his notation that would become lambda. I mean, we don't have x anymore, so you just say lambda dot, and then 0 means I'm referring to the most recently bound variable, the most recent binder working out. Okay? Free variables are unaffected by this scheme. We still call them y or whatever. Terms like this, well, yeah, that becomes lambda 0, lambda 0. This one makes things a little bit clearer. So here, I declare 3 binders, lambda, 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 and then to refer to x, so if I had a 0 here, that would be referring to the z. If I had a 1, that would be referring to the y. And the 2 here means that I'm referring to the x. Okay? So this is an unambiguous way to capture these bound variables. And with a more complicated term, yeah, you end up with more complicated terms as well. So yeah, the idea is that if you represent your terms like this, you don't have to worry about alpha equivalence at all. why doesn't everybody use this? Well, the fact is that actually humans are pretty good at dealing with names. Algorithms actually in practice isn't that hard. Dealing with numbers like this is actually much more foreign to the human brain. Machines sometimes work with this kind of representation, but for humans, we're better off dealing with algorithms actually. Okay, so I want to move on then to the second section on the semantics of the Lambda calculus. Just give your brains a little rest with a silly cartoon. Okay, so semantics of Lambda calculus. So in languages like Java, you can look at all these operational rules that say what do these Java commands do, and you've got these. We've seen I think some small step semantics, perhaps some big step semantics as well, and you see things like this where you've got to carry around a state, evolution of the if statement there, then if true becomes just the statement, if false becomes skip. And there are, I mean, this is just 3 of the rules. There are probably about 1,000 rules for the Java language. It's a massive beast of a language. For the Lambda calculus, you have pretty much just one rule, which is pretty glorious. So this rule is called beta reduction. All it says is that if you have a function, say lambda x returns m, and there's an argument around, say n, then beta reduction says go ahead and substitute that argument in for x inside the function body. Okay, so basically, go ahead and apply the function. And that's the only rule that defines how the Lambda calculus works. It's not quite the only rule. There are a couple of other rules. But okay, I should say, this thing here, so this, whenever you have a function here and an argument, we'll call that a redex, which is short, I think, for a reducible expression. So it's just a thing that you can beta reduce. It's called a redex. So there are actually a couple more rules, but they're very uninteresting. This rule says that if you're trying to evaluate a lambda term that, so lambda x dot m, then you can just consider the m bit and beta reduce that, and then plug that back in to the bigger context that included the lambda x. So it's basically saying you can do beta reduction inside your bigger term. And this rule is basically the same idea. If you've got a big term, mn, and you're trying to beta reduce it, well, just try and beta reduce m, if you like, if you can manage that. Then substitute that back in, and n stays the same. So again, you're just beta reducing inside some bigger context. And again, so this one was beta reducing the function bit. We can also beta reduce the argument bit, so the n bit can be beta reduced. But all of these 3 rules are very uninteresting. They're just saying, do beta reduction at some deep inside your lambda term, and that's fine. And there's one more very, very uninteresting rule, which is just saying, at any point when you're doing beta reduction, you can rename some bound variables. So perhaps to beta reduce m, I might do some renaming some bound variables to m prime, then do the actual beta reduction, and then again rename some more bound variable methods. So, but the thing about alpha equivalence is we tend just not to think about it. Like go ahead and rename bound variables whenever you like. So all of these rules down here, not very interesting. This is the key rule. So I want to show you just a couple of examples of doing beta reduction. So here's my sample term here. I have a function that takes x and returns x applied to x. And my argument is the function that takes x and returns y applied to z. Okay, so just a contrived lambda term I just came up with. Let's see what happens if we do beta reduction on this. So we can substitute in this argument for this parameter x. If we do that, then we end up with this. You agree? I think I did that right. So this says we have two copies of whatever we substituted in for x, and we see that here. Two copies of this argument. So I think I did that right. And we can beta reduce further. We could beta reduce this z, can go in for x. If we do that, then we end up with just the result of this function, which just is it just constantly returns 1. So this function here ignores its argument and just returns 1. So that's what's happened here. We can do more beta reduction over here. Again, it's the same thing. We're just substituting z in for x, which just gives us y, and we can't really go. There are a couple of places, though, where we actually had a choice of different directions we could have gone. We actually noticed. Here, rather than reducing this term, we could have reduced this term. Substitute z in for x here. That would have resulted in that term. So we see that the lambda calculus is not deterministic, or at least beta reduction in its purest form is not deterministic. There are many paths you could take. However, there's this interesting thing. If we were to carry on here and beta reduce again, so z goes in for x, then we actually end up at the same term, which is interesting. There's another possibility right up at the top. We could have shoved z in for x right up at the start. That would have ended up with a term like this. And if we'd have done another beta reduction on there, we'd see we'd get y put in for x, so y. And again, we'd have ended up all at the same term. So we're seeing with these beta reductions, there are many different branches you can explore when you're doing a beta reduction, but it seems, at least on this example, we always seem to end up at the same answer. So there you go. So key concept, beta reduction. So just before I go any further, there's a handy thing to have around is we've got this relation of beta reduction. This just represents doing a single step in the evaluation of your lambda term. It's also quite handy often to be able to talk about doing lots and lots of consecutive steps. And so I've defined the reflexive transitive closure of the beta reduction. So this basically captures 0 or more consecutive beta reductions. And that's defined formally like this, but it's basically a chain of beta reductions. It's nothing different. Using this multi-step beta reduction, we can have a rather interesting theorem about the lambda calculus, which relates to this property that we sort of hinted at in the previous example. It's called confluence, and it was discovered by Church and Russell. And the theorem says that if you have a lambda term m, and you can go in a chain of beta reductions to some other lambda term, say m1, and it's also possible to go via some chain of beta reductions to m2, then there would exist some further lambda term m prime, such that m1 will eventually get you back to m prime, and m2 will also get you back to m prime eventually. So this is a very geometric theorem, so it's best visualized as a picture. We're saying if we start at our lambda term m, and we can take a few steps to get to m1, and we can also take 0 or more steps and get to m2, then it's always possible to do some further steps from those 2 points and converge again. And if there's time next lecture, it certainly won't be this lecture, I'll make a couple of remarks on how you might go about proving this theorem. It's jolly difficult. And just trying to work out where to stop, because I think it's almost time up. Yes, I think I'll just do one more slide and then we'll stop. So, there's one more concept, and this is called beta normal form. And this is the idea that if you have a lambda term that where you can do no further beta reduction, there are no more redexes for that jargon, then you say that lambda term is in beta normal form. It's a little bit like saying it's a value. And we'll say that a lambda term has a beta normal form if it reduces to a beta normal form. And there's a theorem that says that if a lambda term m beta reduces to some normal form n1, and it also reduces to some normal form n2, so both of these terms that they reduce to are in beta normal form, then they must be the same normal form. Okay? So if you can hit a normal form, you will only ever hit the same the same beta normal form. And the proof of that is pretty straightforward, actually. So by the Church-Rosser theorem, which said that if we separated, we can always meet again later, we know that since here, suppose we've separated, we started at m, we went down to n1, and then we separated also, we went down to n2. By Church-Rosser, we know that we will be able to meet again later on. That's what Church-Rosser says. However, n1 and n2 are already in normal form, so we know that in fact there's nowhere further to go from n1 and n2. So the only way that you could actually converge again from n1 and n2 is if n1 and n2 are already the same. And that's what this is saying here. It's actually quite simple proof. And I'm going to leave it there. Okay? So as a quick advertisement for coming to the next lecture, which is at the slightly less appealing time of 9 o'clock, what you will look forward to is some lambda terms that don't have a beta normal form, some lambda terms that do have a beta normal form, but sometimes don't, and I'll say a few remarks on how you can prove the Church-Rosser theorem, which is a very cool geometric picture type of proof. And also we'll go on to the real meat of this couple of lectures, which is how you can encode arithmetic, control flow, while statements, recursion and multiplication, everything like that, all in the Lambda calculus. So that's in the next lecture. Thank you very much.